Okay, so my name is Eduardo. Hi all. I'm going to present on behalf of my team, which is also comprised of Mateus, which is here, and Tan Hall, who unfortunately couldn't join. So the agenda for our presentation is just a background, a summary, then talk about the features and the engineering steps that we took before starting to actually modeling the competition. Then the changes that we made in the model architecture that were key for us, and the training methods. So as a to start here in the feature selection engineering. So basically, before we start modeling anything, we were quite surprised that the graphs were that big. So we had worked with GCNNs and graph convolution networks before, but usually in very small graphs, and the networks themselves are also very, very small. So it was really efficient to train those types of models. But in this competition, we found that like the graphs were huge and took a lot of memory, especially to store the gradients during training. So we took a few steps in the first 2 weeks that we also think is important to mention here, because this allowed us to optimize a lot our training code and our procedure, and basically get some fast feedback loop between our experiments. And this was like key for us to get good results, I think. So the first thing that we did was to prune the graphs. So we noticed that for layout, so just a few nodes are usually configurable, which is the dot, reshape, and the convolution, usually. But a lot of the network itself is not configurable. So it means that across a set of configs, most of the network is always the same, it doesn't change. So we did kind of like the first idea that we had here was to prune the graph in a very simple way, where we only keep the configurable nodes themselves and the first degree neighbors to those nodes as well. So the idea is that a configurable node can also depend on a neighbor. So we also wanted to keep the neighbor. And our idea was to iterate on this and see if like second and third degree neighbors could also help. But in the end, we found that only the first was already sufficient. And this reduced our VRun usage a lot, and also sped up some trains 4 to 5 times. And we didn't find any loss of accuracy or any Kendall-Tau metric or anything due to this pruning. So this was implemented in the first week, and then we kept using the pruning graphs for layout. Another thing that we noticed is that a lot of the configurations in the layout were duplicated, like exactly the same config with a different runtime. So we were a bit afraid that this could introduce a lot of noise and also bias the network towards those duplicated configs, because they could be seen much more than other ones that are unique. So we opt for simply removing the duplicated ones, and we just kept the unique kind of at random. We tried also to use the runtime, like the median runtime of all the duplicated ones, but we didn't find any improvements by that. So we just did the simple way and just removed the duplicated. We noticed that this improved the accuracy a little bit. It was not any huge gains by no means, but more importantly, the training was much more stable, like the curves for the metrics. So we definitely kept this. And thirdly, we did some compression for the layout config fits, because those features are usually 18-dimensional vector, 6 for inputs, 6 for output, and 6 for kernel. And we noticed that the issue would be that usually these are very sparse, as in is just the number of the configurable nodes. But then to train a model, we need to get this vector to a dense state and replicate stuff like these 18 vectors for all the nodes in the graph. And this will take a lot of RAM as well. So Mateus had an amazing idea that he noticed that these 18 vectors can only have 7 possible values. So instead of having a 6-dimensional vector for inputs, outputs, and kernel, we could just have a single integer which is in the base of 7 that can represent those 6 dimensions. So this allows us to load all the networks, the configs into the memory, and basically train without any bottleneck from I/O and preprocessing. Because before we noticed that our GPUs were always going to 0 because there was a lot of bottlenecking of loading data from disk and sort of stuff. But by doing this, we managed to remove all the bottlenecks, and the training was super fast. And those three tricks, the duplication, the pruning, and the compression, allows us to train model from 40 minutes to 1 hour and 20, more or less, depending on the configs, which allows us to basically iterate super fast. So another thing, still on the data that we changed, that also gave a tiny boost, is that we noticed that for the node fit, the last features from the 134th forward, they were 0 padded, but this pad was a bit ambiguous because those features were related to the index, and 0 is a valid number. So having also a 0 padding is kind of weird. And also we noticed that the same kind of features for the config fit were -1 padded, which made kind of inconsistent between the two. So we regenerated all the node feeds to be -1 padded, similarly to the node config feeds. And this allows us also to use the same embedding matrix for both, which is something that improved a bit. And then for the pre-processing, for layout, we just use a standard scaler for the first 134 features of the node feed. The scaler itself is really important because those features can be something like the shape of a tensor that can have like big values. And also there are some features which are the products and sums of those dimensions. So this can go quite big and then could completely disrupt the training. So having a scaler here, as with any tabular data, is very important. And then for the ones that are just permutation of indexes, we use embedding matrix, like I said. We concatenate the left ones for the node feed and the 18 ones for the config feeds, and then we pass those under a single embedding matrix. And then for tile, we just do late fusion with the config feed into the network. Talking about a bit now about the model architecture. So this is the overall view of our layouts model. So here's how we preprocess the data. As I said, the first features go into a standard scaler, and the ones related to the axis indexes, they go to a embedding matrix of only 4 channels. And the opcode for each node goes to another unique embedding layer with 16 channels. We noticed that using 16 channels here improves quite a bit, because otherwise this could be underrepresented if we use something like 1 channel or 2 channels for this, and it's quite important. Then we concat everything to get a tensor, which is number of configs, number of nodes in the graph, and 276 channels. Then we have a first linear block just to embed these raw features into embedding. And then we proceed with 2 convolutional blocks. I'll explain the blocks in more detail later. And then finally, after the convolutions, we have a global average pooling. These will basically reduce the graph into single vector. And then we have finally the linear with the log limits. So here's a bit more about the features that I just explained. And here a bit more about the blocks. So the linear block and the GCNN block is the same architecture pretty much, which one thing that changes is the convolutional or the MLP, the linear layer. So we created those blocks kind of following the logic that we had for computer vision and borrowing some ideas as well from NLP. So we start by doing a pre-normalization. We use instance norm for this. Then we apply the convolution itself. We found that SageConv worked very well for this data. We tried get and other layers, but they didn't work that well. One assumption that I have for get is that get usually does attention in the graph connections itself. But for our product, our problem here, the graph itself is pretty well defined, so there's no noisy connections. So the GAT didn't help that much. The SageCon was much better. Then we follow the convolution by a self-attention layer. The idea of this attention layer is very similar to squeeze and citation from convolutions, which you pretty much have a vector. Then you squeeze the channels dimension by using MLP. You bottleneck it to reduce by a factor of 8, could be the channels, and then increase it again. And the idea of that is that you capture the correlation between the channels, and then we apply a sigmoid to normalize between 0 and 1 and multiply by the original vector. The idea is that the MLP will capture the correlation between channels, and then by multiplying this to the original one, you are suppressing channels that are very similar to each other, while you could be enhancing channels that are quite promising for the final result. And this self-attention, we noticed that also didn't give a huge boost, but was another piece that gave a time plus that in the end, when we add all those tiny improvements, they add up quite a bit. Then we followed by the cross-config attention, and this was the one that I think gave us the huge boost for the default collections. And the idea behind this is that we noticed that the ranking losses were a must in this competition, but it felt a bit weird to only compare the different configs in the very end of the network, because it was only being compared implicitly via the loss function, but not explicitly in the network itself. So we had this idea of doing this very simple attention, where we basically divide the elements, each element in the tensor by a temperature. This is usual for softmax temperature, and then we do the softmax across all configs in the batch. And the idea here is that, like, for each element of like each particular node and each particular channel, we will compare with the, let's say, the competitors, the other possible configs, and then we will rescore, we will recalibrate based on the batch itself. One thing that we noticed when we introduced this is that directly improve the results, but one kind of side effect of this is that the embeddings were getting too similar, because we were always kind of like using the whole batch to create the features. So we came up with this follow-up idea of just doing this on half of the vectors in the layer, and then concatenating with the input itself. So we would get the benefits of comparing against other configs, but also keeping the individually of each config. And then finally, we have the nonlinear activation function, and then we have the residual connection. This is our block pretty much. And then for training, we basically, from layouts, we sample some configs from each graph and create a batch only with those configs. So we don't mixture in a single batch different graphs, basically. And then we use pairwise hinge loss. We tried different loss functions. This was by far the one that improved most of the results. And in the end, we opted to use ensembles, not only because of the improvement of results, but also due to stability. We're quite afraid of a shakeup. So the ensemble really helped with the stability, as we had seen in previous competition and from experience. Now, very quickly to finish the things that we tried that didn't work. So we tried to mix together the random and default data, but this didn't improve the results. Also, we tried second level stacking models on top of the prediction and embeddings of our ensemble. This pretty much helped a lot locally, but not that much on the leaderboard, neither private nor public. Pseudo labeling also didn't help. Fine tuning on specific graphs because of the number of nodes, we could know more or less which graph it was in the test set. So we try and fine tuning the models on those target graphs, but didn't help. Helped a lot on local, but not on leaderboards. We tried a lot of ways to sample the config as well, like making sure that in the beginning, the runtime between the configs are sparse, so it's easy samples basically. And then by the end of the training, we start to get only very similar in terms of runtime configs. So it makes it harder for the model, but this also didn't help. Other loss functions, as I mentioned, and gradient accumulation and training with more than one graph also didn't work. That's pretty much it for my for our presentation. Any questions?